Given n as the number of nodes and an array of the edges of a graph, find out if the graph is a valid tree. So we have a number of nodes, n, denoted by n, and an array of the edges, and it's highlighted, so it's called edges of a graph. Find out if the graph is a valid tree. The nodes of the graph are labeled from 0 to n minus 1, and for every entry in our edges array, we have it in this format, and it represents an edge, an undirected edge, connecting the nodes x and y of the graph. Now, our graph is a valid tree when all the nodes are connected. So that means there's a path from any one node to any other node, and there is no cycle between them. All right. Now, these are some examples. So we have these edges, and this represents a connection between 0 and 1, 0 and 2, 0 and 3, and 3 and 4. As you can see, 0 and 1, 0 and 2, 0, 3, and 0 and 4. Okay. And n equals 5 means there are 5 nodes in the graph. And since all of them are connected, there's a path from any one node to any other node. And there are no cycles in the graph. The output for our function that they want us to make will be true. Now, in this case, we have n equals 5, so 5 nodes, starting from 0 through 4. And these are all the connections between them. However, we notice there's a cycle. There's 0, 4, and then 0, 3, and then 3, 4. So that forms a cycle. So this is not a valid tree. And so we're going to return false. Lastly, we have this example here that is also a valid tree. You can go to every single node from any one node, and there are no cycles between them. Okay. Now, for the solution, we are exploring a variety of graph algorithms, and this one is going to be one we explore with a depth-first search approach. But it can also be breadth first search. So, but the depth first search is fairly straightforward. And so, for the graph to be a valid tree, the number of edges must equal n negative 1. If the total number of edges is less than n negative 1, not all the graphs are connected, which defies the property of a tree. Similarly, more edges will mean that there is a cycle in the graph, therefore it is not a tree. So, in this example, that is not a valid tree. We can see we have 5 nodes, so 0 through 4. However, the edge count is 3. So it's supposed to be equal to 4, like if it's going to be a valid tree. So we can just deduce automatically that, oh, this isn't a valid tree. No need to start even looking into the tree. Once there's a mismatch there, you already know that there's a problem. Now in this case, there's a cycle, so we have way more edges than we should, right? So edges.length is equal to 1, 2, 3, 4, 5 is equal to n, but it should be equal to n minus 1. And so therefore, we know there's a cycle, it's not a tree. Okay, so that's like a base case for breaking out of this algorithm. And I think we can, we'll soon show the code and hop back and forth between them. But let's look at this blob of text that might make things, make it useful for us, like looking at the code. So for the base case, return false if the number of edges is not equal to negative n minus 1. And so we have this solution right here, actually, this one right here. And if it doesn't equal n minus 1, just return false. We don't have a valid tree. So that's what that is. Otherwise, create an adjacency matrix of n minus 1, where adjacency index, every entry in the adjacency matrix will represent the array of all graph nodes from which node I is connected. So we're constructing the graph in code. And that looks like this here, right? So we're using a grid in this case, not a map, right? We've done a map before, but this time we're using a grid, I think for the sake of diversity, because either one works. I think I'm more of a fan of using a map. So this is like a JavaScript shorthand, or well, pattern to create an array of size n. And this is just TypeScript gobbledygook. But it seeds every entry in the array with an empty array, so an array of arrays. And in this case, an array of empty arrays of size n. Okay? Now, this is where we're building the graph. This is equivalent to essentially this, right? This image. This is like a visual thing. But how do you represent this visual thing in code? When we have the edges like this. That's what this is doing right here. Okay? And then What else? What else? What else? Next, we initialize a visited set and a stack. And so initialize a visited set and a stack. We do that here. And this is how you do it in JavaScript slash TypeScript land. And we're initializing the stack with 0, right? The 0th node. And then we're also seeding the set. Like, oh, we've seen the very first entry in our tree because we know it goes from 0. It always starts from 0. That's part of the constraints of the problem. And so we do this here, just like they said. And then we start exploring the graph from node 0. Using a depth-first search approach, we traverse the graph, visiting each node and marking it as visited. So that's our end game. We want to mark each node as visited once we've seen it. If we encounter a neighbor that hasn't been visited, we add it to the visited set, push it onto the stack for further exploration. Okay. Finally, after completing the DFS traversal, we check if all nodes have been visited. Okay. Ultimately, we will verify that the graph is fully connected and no cycles exist by comparing the length of the visited set and the n number of nodes and the n number of nodes. And there's an illustration to help us get better, like understand things better. And so we have this graph right here. So the first check, oh, are they equal? If they are, then we shall proceed. Right. So they construct an adjacency matrix and populate it with the neighbor nodes. So using these, right? That's what this function here does. And next we have our stack. We seed at the stack and visited with the 0th node. And now we pop from the stack. So that all that happens in here, right? And so while there's something in the stack, remember we've seeded it, we take the first thing out of there. Then that thing, we're going to check all its neighbors. We want to loop through all its neighbors. And I believe they do that here. Okay, so 0's neighbors are 1, 2, and 3, as we can see here. And you can see that in here as well in the adjacency, in this adjacency matrix. So you just index at 0 here and take everything you see, which corresponds to all the neighbors. And again, it's bidirectional, right? It's connected both ways. So that's why you see that each of these also has 0 in their list of neighbors. And so we add it to the stack, add them to the stack. If we haven't seen them before, So we're going to add them to the set. Oh, now we've seen them. And now we'll push every single one of them into the stack. And the stack that became empty here at the end of the day is no longer empty. So this loop is gonna go again and then take the next thing. Okay, so we had just popped 0 from the stack. Now all its neighbors get pushed onto the stack and they all get visited as well. And we start evaluating neighbors from here. So the last thing in is the first one out. And so we're gonna get 3 out of there, because it's a stack, and its neighbors will be checked. So we're going to look up 3. We've seen 0 before, so that's not going to do anything when we're looping through the neighbors in here, right? Because we've seen 0, 0 is the first thing we saw. But now, the next thing though, 4, we haven't seen that guy before. So add him to the stack. Is the last thing added to the stack. Say, oh, we've seen this before in the visited. And then we go again. We're at the end of the loop here. And so we can come back here because there's still stuff in the stack. And we just keep doing that till we're done. So take 4 out there, check its neighbors. 3. Have we seen 3 before? Yeah. Next 2. Have we seen 2 before? Next 1. Have we seen 1 before? Yes, we have. And now we have visited every single node. We've checked every single node in our tree. And now, lastly, all we do is just do this check. So, do they match? Well, first of all, we've made sure we've touched every single thing in the tree, with every single connected thing. So, visited holds every single connected node, right? Pay attention to that. Every single connected node. That's what we've populated visited with. That's what visited is supposed to hold. And now, that was our goal at the end of the day, because those are the 2 conditions. The first condition is if the edges don't match, aren't what they should be, return false. And now, in this case, if the amount of connected nodes don't equal n, it means there are some disconnected nodes and it's not a valid tree. Or if it's bigger, right? If the number of things we visited is actually no. That's all there is to it, right? This just tells us if everything is connected or not. That's what this condition tells us. And that's what we're looking for. And that's all there is to this problem. Now I wanted to point something out. at the end of this video. So if you've watched the previous video on cloning graphs, I presented a recursive depth-first search traversal. Now, every single recursive depth-first search DFS can be done iteratively, and so this solution is done iteratively. Okay, all right, with iteration. And so, but you will always need a stack to do it because it simulates the recursive call stack, right? Every function has a call stack, so you can instead initialize a stack and loop through things iteratively like so. And I went through the stress to make a recursive version of this problem. And so this is our recursive helper. All it's doing, the goal of looping here is to visit every single node, right? Every single connected node. And so once you do that, once you visit every single connected node, well, connected, you can do that recursively instead of with the loop, this loop on the while stack here that we're using. We can do that. You notice that a lot of, so this is our function, the main valid tree function. Same thing here, we check the edges, initialize the adjacency list that's constructing the graph, initialize the set. The only difference now, I initialize the set as well here. The only difference you'll see is I'm using this function to populate visited, right? That is the list of connected visited holds. Remember, visited holds the list of connected nodes. So I'm using this recursive call to populate the visited array, and I'm passing in the first node, our adjacency list, the entire graph, and the visited set. And in there, all I'm doing is saying, oh, have we seen this before? If we haven't seen it before, oh, say, okay, now we've seen you. And then call it again. It's going to call itself for every single neighbor of that node we just added to the list of connected nodes, right, in the visited set. Okay. And then it's going to update visited by reference because I'm passing it in as a function argument without any cloning. And then I can just do this exact same check down here. So like I said earlier, recursion is for looping through things, right? You can replace almost every loop, if not every loop, probably every loop. I'm sure there's some formal proof to say that you can replace every single loop with a recursive call. So this is just one example. And I also updated the clone graph function with an iterative solution because the first solution I shared was in the last video was recursive. This is an iterative solution that I've added that works. I put it in there and it passed all the tests. So the more of these problems you see, the more intuition you get for recursion, right? The less scared you are of it. And yeah, the more informed, I would say, you are. And so time complexity is O of n, where n is the number of nodes. It's linear time. We're checking every single thing as much as we possibly can. And then the visited has a length of n in the worst case. So space complexity is O of n. All right. See you in the next video. Like, comment, subscribe, share. Thank you so much for watching.